Hello and welcome back. We're going to be continuing our study of inferences with means. So how to create confidence intervals, and eventually tomorrow we'll talk about t-testing, which is just like hypothesis testing, but with inferences with means instead of with proportions. So we've been talking about the central limit theorem, and we've learned that even when our populations are skewed or multimodal or anything that's not nearly normal, we can still use sampling distribution models and the inferences practices that we've learned with proportions as with means as well, as long as our sample size is large enough. So one of the other questions we'll be able to answer is how much should you pay for parking for a parking garage? So how do they set the prices when they decide to take out a loan to build a parking garage? I know at the college that I went to, there was a lot of discussion about how parking was terrible, and they wanted to build a parking lot, just like what you see here, parking garage. And the question was, how much would they have to raise the parking fees, which were already $100 a year? How much would that have to go up in order to be able to pay for the whole project? So we'll be able to answer questions like that, knowing how much revenue that we would generate, how many people would come in, so then how much revenue we would need, and how much we'd have to charge each person. So let me tell you the story behind students' T models. So students' T model is pretty fascinating. So this is Mr. Gosset, and he was a taste tester, an experimental draft brewer for Guinness, which is a brewery in Dublin, Ireland. So he was the taste tester there, so he had a pretty cool job. A long time ago, over 100 years ago, and his job was to taste test a sample of the production for that day, and to make sure that it was good. And if it wasn't good, then they would stop the production, and they would try to figure out what was going wrong. And sometimes, he would have a false positive. So just that one sample that he got gave him values that were unusual if it was still in the normal range, and so he stopped production. That would be a false positive. Well, he had far too many false positives than what he was expecting, and so he wanted to investigate further. Now, because of his health and productivity, he was only limited to taste testing four drinks a day, right? He couldn't really drink any more than that. And he would drink that every single day. So this guy probably had some liver issues, if I had to guess. So he had far too many false positives. So we know from hypothesis testing that when we set our alpha level, which is our level of significance, based on a true null hypothesis, assuming that was true, the probability of us getting a false positive is going to be exactly equal to whatever value we set our alpha level to. So if we have a really strict alpha level of like 1%, then we'd only have 1% false positive. But this also gives us a really strict burden of proof for us to be able to detect a difference or a deviation, or the sensitivity of a test, right? The difference between what we assumed it was, our null hypothesis. So then if we set it at 5%, then 5% of the time we would have false positives. So we would sound the alarm, we'd stop production, and we would figure out what was going on. But 5% of the time there was really no difference, and there was no reason to do that. So it'd be wasting money. If we had a really sloppy alpha of 10%, this would be very sensitive. We're more likely to be able to detect any deviations and the quality of our product for our quality control. But also that means 10% of the time we'd be stopping, and there would be nothing wrong with the production, and that would be wasting money and be inefficient. So what value do we set this alpha level at? Well, it depends on what percent of the time you're okay with having bad product go out, or something along the lines of that. So remember, this setting this value depends entirely upon the severity of the case. So if we're talking about life or death, or like sentencing, like death penalty, we want it to be less than 1%, right? Even more strict, because we'd be terrified of the prospect of having 1% of innocent people being on death row. That would be terrifying, right? But if we're talking about candy, like our M&Ms that we did earlier, that doesn't really matter, right? If we're wrong 10% of the time, that might make us look kind of like a jerk, but that's okay. It doesn't really matter, because we're only talking about M&Ms. But our default alpha level most of the time is just going to be 5%, which is kind of a happy medium. So on this one, he probably had an alpha level of 5%. Maybe it was 1% or something like that. But he ended up coming back with 3 times as many false positives as he thought he would get. Now, he was using a standard normal model, which is how everyone before him, that's all everyone knew. Just like with proportions, we use normal models with means, and they thought that's what we were supposed to do. Well, he was one of the first ones to discover, in fact, that there was a difference. When we do means, and especially when we have small samples, we can't use a standard normal model. So his model became known as a t distribution model or a student's model. The reason for that is whenever he went off to publish, he tried to publish his work after he studied statistics, Guinness wouldn't let him publish it under his name, and so out of fear that somebody would tie it to the brewery business and that it would give the competitors an unfair advantage, or that Guinness would lose their advantage. So he had to post or publish all of his work under a pseudonym of student, so that no one could tie it to him and to the brewery and to the actual process that they were using it to. So even today it's known as student's distribution, and the T model is from the student as well. All right, so his model, if we look here, this dashed line here, this is a normal model, okay, our standard normal model. These other 2 lines here with these degrees of freedom, that's just, the degrees of freedom is simply 1 minus our sample size. So if we're sampling means with a infinite degrees of freedom, so an infinite sample size, then it would truly actually be a normal model. But when we have much smaller sample sizes, like in his case, he had a sample size of 4, so the degrees of freedom was simply 3. So his model actually looks something like this, the solid line here. And as we can see, if we were expecting going for 5%, an alpha level of 5%, which is about right here, he would expect, let me see if I can draw that, he would expect this area right here to be 5% of the time he had a false positive, right? But what he actually ended up with was 15% false positive. So that's because the actual curve looked something more like this, which was 15% instead of the original 5% that he thought it was. And that's why he was able to discover that he was using the wrong model all along, and he needed to come up with the new flatter models or family of models that are similar to the bell curves but are flatter depending on your degrees of freedom. And that's pretty much how it was done. It was all through because of this guy, and he went and he studied it, and I'll tell you more about the story in just a bit. But this family of models is called T distribution models, and they're all the parameter for them is the degrees of freedom, and the degrees of freedom is 1 minus the sample size. So with him, he was only allowed to drink 4 glasses a day. 4 drinks a day, and so his sample size would be 4, degrees of freedom would be 4 minus 1, which is 3. So that's this model here, and as you can see, it's much flatter, right? So that means that the area under the curve, the false positive, would be much higher. So he would actually have to set his critical value much further back in order to only have 5%. So instead of going about 2 standard deviations out, he would have to go, so obviously that was wrong, but he'd have to go much further out, maybe 3 or 3.5 standard deviations in order to be considered an unusual sample. All right, so in statistical inference, we have sampling distribution models, which comes from the central limit theorem. It's basically with a certain sample size, what would we expect the variation between samples to be, and what would be gives us a metric using the normal model, the sampling distribution model, to decide if something is unusual or not. Confidence intervals are based off of our samples. When we don't know the actual true population parameters, then we use confidence intervals to create an interval with a certain margin of error based on our critical value to be able to try to determine what range of values we think the true proportion or the true mean or parameter in general is going to be. Then hypothesis testing allows us to set a null hypothesis, and if that null was true, then what is the probability that we have a sample statistic that we did, or more extreme, using normal models or using students' T models when we're talking about means. So normal models are for proportions, and when we're talking about means, we're going to have to use students' T models. So the sampling distribution models were based off a sampling distribution. This is when we know the true proportion. or the true parameter in this case. And that allows us to give us the sampling distribution model, which is distribution of all possible samples of a certain sample size n. Once we find when we don't have the true proportion, we're trying to estimate it, then we use a confidence interval. So if our proportion, our sample proportion was 52%, notice this whole thing is going to be shift off the 50% in the middle. So it's 2% off, right? And what we would do is we go out 2 standard deviations in both directions from the sampling distribution model of this sample size using the standard error instead of the standard deviation, which is always slightly off because we use the sample proportions instead of the true proportions, because again, we didn't know the true proportion. All right, so then once you create a 95% confidence interval by going out our margin of errors, we're 95% confident we've captured true proportion, meaning 95% of samples gathered in confidence intervals created using this method would successfully capture the true proportion. All right, so our confidence interval is formed by taking our sample plus or minus some critical value, which we get from the inverse normal functions, multiplied by the standard error, which is calculated just like the sampling distribution model, standard deviation, but using our sample instead of the true proportion. All right, so this is why trying to explain why his models were flatter than the normal model. So it's all because of how the standard deviation is calculated. So in our population, so this is the actual true population, and we don't know what that population is. We're trying to make estimates and inferences about the population based on our samples. So in the actual population, we have 2 parameters. We have the mean, which is mu, and we have the standard deviation, which is the sigma. So let's say that our mean was, or mu in this case was 20, and the standard deviation we'll just say was 5. Now this is of course a skewed distribution, so the standard deviation is not going to be a very good metric of what the spread is, because we're normally thinking with standard deviations normal models, where in this case we're probably not likely to have the empirical rule work with 68% lying within one standard deviation, so between 15 and 25, because the data is so far skewed, and it's skewed by these outliers on the right tail, right? Okay, so when we sample from the population, we're also going to occasionally get these outliers that are going to skew those sample means and those sample standard deviations as well. So here are 3 different samples from this population. Now the first sample, this all looks pretty close to what's going on here, but then notice we have this really far outlier. We just so happen to get one of those rare outliers. And what did that do to our sample mean? Well, the population mean is this red line here. That's the 20. But this individual sample, this green line, had a mean that was much higher than the original population mean. Why did it have one that was much higher? Because it didn't have as many of these, but it did have one of these outliers. So the normal numbers were what we would expect, but because we had one of the outliers, it caused the sample's mean to be much higher than the original one. But that's okay. We expect means to vary from sample to sample. All right, on the next one, notice here, these are all the normal values that we would expect here, but there were no outliers that we got on this one, because those outliers are rare. Occasionally they happen like here, but they didn't happen on this one. See how these categories are much wider? That tells me there wasn't one on the outside like we did over here. See those categories? The bins are much smaller. All right, so that's because they resized it to fit. Anyway, so what happens there, because we didn't have any outliers to skew to the right, is that our mean, which was much smaller than the actual population mean. Remember the red one here is a population mean. Our sample is smaller. Okay, so another one here. This one had a bunch that were on the small end, like we'd expect the mode over here, but very few and almost no outliers in this case. So now it's in just like this one, but even more extreme. So our sample's mean is much less than the original mean here. Now the problem arises is when we take the standard deviation from that. So when we take the standard deviation of our sample, it's not going to be the same as the standard deviation from the population, unless our sample size was so large that it really accurately represented the population. But with small samples, there's going to be a big difference, and that's where this model comes in. So the reason for that is, remember when we calculate standard deviation, first we find the deviation from the mean. Now, each one of these values, they're going to deviate from the mean, the sample mean, the green bar here. But we shouldn't actually be calculating the difference between the values and the green bar, the samples mean, we should be calculating the difference between the sample values and the population's mean, which is the red bar. That is a huge, huge point. Now, sometimes when they're really close, it doesn't make much of a difference. But when it's so far off, when we're calculating the standard deviation from the sample's mean instead of the population's mean, because we don't know what the population mean is, then that's going to give us a large difference because we don't know what this population mean is. And remember, with samples, they're always going to have a smaller standard deviation and be closer to their own sample average than the population's average. So think about it like this. If we took 10 American males, right, their average, each one of those men are going to be closer to the sample's average than the average population or the population's average. So let's say the average American male man is, I don't know, male men, are they really tall, or I'm making a joke, like UPS mailman. So let's say it's 6 foot tall, but let's say that our sample just so happened to be much shorter, or let's say it was much taller. So we just so happened to sample a lot of basketball players. So their sample mean was 6'4". Now, if I calculate the standard deviation based off of their sample, which was higher than the actual American male sample of 6 foot, then the standard deviation is going to show up as being a lot less than what it should have been if we calculate it from the true sample mean. But the problem is we don't know the true sample mean. Okay, so how do we correct this? Well, we end up using a new set of models. Instead of a normal model, which is the blue line, we end up with a flatter t-distribution, which is parameterized by the degrees of freedom depending on the sample size, just n-1 in that case, and it's going to be a flatter model. And the reason it's flatter is because it's always going to have a smaller standard deviation than when it's calculated by it using its own mean, sample mean, instead of the population's mean. So I know I've talked a lot, and I really hope that all made sense. I will definitely repeat it again, but there's some really, really cool stuff going on there. We've actually seen this concept before. Let me go ahead and go to the next one here. So the Gosset was the first person to differentiate between the two parameters, S, which is the standard deviation of the sample, sometimes written as S of X, and sigma of X, which is the standard deviation of the population. So when we take a sample and so for instance, if we put a bunch of data into the calculator, so I'm going to go to stat list, and here I'm just going to put a bunch of values here. All right, so just a bunch of random values. And if I run a one variable statistics, so we'll go to stat, calculate one variable stats off of list one, good to go. All right, so if we notice here, there are two different values that are given for the standard deviation. One is the S of X and one is the sigma of X. That's what this is talking about here. Do you remember which one we always used? I know you're like screaming at the screen or at your phone, and I can definitely hear you, so don't stop screaming at me. I love it when you guys talk to me because I'm really lonely. So on this one, S of X, that's the one for the sample. And we always use that one, and it's usually the one that we want because we rarely ever know the actual population. That would be if we took a census. We don't take censuses very often. It's usually a sample, so there's one more degree of freedom, one more parameter that we're estimating for. So instead of dividing by n, we divide by n-1, and that's why the S of X is always going to be slightly larger than the sigma of X if it was a true population. So this differentiation between a sample's the standard deviation of a sample and the standard deviation of a population, we have Gosset to thank for that. All right, so his distribution, as we notice, if the degrees of freedom goes to infinity, meaning we have an infinite sample size, or the census, the population itself, then we could use a normal model, which rarely is the case. Or if we know the actual population parameters, we use a normal model like we did with sampling distribution models from chapter 17. But that's really rare. We're almost always using inference, using samples to try to make conclusions about the population. It's some of that like only God knows type stuff, right? All right, so then degrees of freedom of 3, 2, or 1 is going to be very flat. And then as we get a larger number of degrees of freedom, it doesn't change that much. Let me show you a nice little applet. This is from GeoGebra. So this will allow us to change the degrees of freedom and see how that changes our actual our model. So here, this purple is going to be the normal model, standard normal model. The red here is going to be Gosset's t distributions with a degree of freedom of 1, which is the smallest one, which would mean that we were taking a sample size of 2. So like finding the average heights of 2 people and using that to estimate the height for all Americans or something like that. So notice that this is very far different from the actual standard normal model, and the tails are much wider and it's much flatter as well. But as we increase our sample sizes, so now let's say degrees of freedom of 2, certainly a sample size of 3, it's becoming closer, right? Keep going and going and going, and eventually it gets so close, like a sample size of 22 with 21 degrees of freedom, it's really close to the normal model. So we might not even detect a difference between that. But the reason he was able to see that there was something wrong going on here was because he had a small sample of only 4. Degrees of freedom of 3 because a sample size of 4, because he was limited to only being able to have 4 drinks a day because of his health and productivity. So anyway, that is just kind of a visualization. If we have a sample size of 100 or more, at that point, there's hardly any difference. But for due diligence sake, because we have it and just putting in the technology, always use the degrees of freedom. Don't use the normal model when we're sampling with means. But you won't notice much of a difference when we have larger samples. All right, so how did he do this? It's kind of a fun day because you get to talk about a lot of history. I also did the space math video earlier today, which was really cool. It's kind of geared towards geometry, but you might check it out if you have time or if you're bored. I'm sure you guys are all working full time, right now. So anyway, might check it out. It's kind of cool. Literally NASA math going on with geometry kids right now. So how did he simulate the difference? Well, first he needed to have a population. So where did he find a population of 3,000 volunteers? Well, he went to the local prisons, which is kind of funny. In Ireland, with all the drunken bar fights, which is totally not a stereotype. I'm kind of like Irish, so I can say stuff like this, but I mean, my name's Ryan Murphy. You can make it more Irish if you said Ryan Murphy, but anyway, so he went to a prison and he recorded the heights of 3,000 prisoners there, and he wrote them down on note cards. That was his population, and he shuffled that and he sampled 750 different samples of 4 of those cards. And after each, so he grabbed 4 of those cards, he found the average, he wrote down the average and the standard deviation, calculated it all by hand, and then he did that again and again, and shuffled in between each time, and again, 750 separate samples. He took all those means, put them all together, just like we have in the sampling distribution here, and then from that he was able to create very accurately the Gosset distribution T model with degrees of freedom of 3, because again, sample size of 4 minus 1 is 3. So this solid black line here, he was able to approximate that very, very close because of the amount of precision that he did. Now, this process took him over a year to complete, which is insane. He was messing around with the same 3,000 note cards and calculating these averages by hand, which is not fun. We don't even like doing it in the calculator, but he did it all by hand. It took him over a year. We can make simulations like that in a matter of seconds now. But anyway, so over 100 years ago, he discovered that and he found this model, but it was only for sample sizes of 4. And there's infinitely many, it's a whole family of these models. And so there was no way he was going to be able to do that. So he went back to the drawing board, and eventually they were able to come up with how to mathematically produce all those models without having to simulate them, come up with them like he did. All right, so you should have your assignment if you want to go ahead and print that out. I've posted it as well. So follow around here. I'm going to read this first paragraph because it's really important. So what are we doing when we take inferences based on sample means? So we often don't know the standard deviation of the population. We don't know the mean or the standard deviation of the population. So we're having to use inference models to be able to inferential statistics to make inferences about the population. That's called sampling. That's what stats is all about. So just like how the sampling distribution model for proportions are based on the true proportion, we often don't know the true proportions. So we use the next best thing, which is for our inferences, which is our sample. From this, we create we're able to create a confidence interval from using the standard error, right? The error is to remind us that it was based on the sample and not on the actual true proportion itself, because we didn't know what that was. So the true proportion was 50%, our sample was 52%. So as far as we know, the true proportion is 52%. But we know it's not exactly 52, but that's our best guess because it came from our largest sample. So from that, we were able to create a confidence interval using the standard error formula. Remember the p hat and q hat, so the true proportion. So even though this is the sampling distribution model of all possible samples based on the true proportion of 50%, if we don't know that, we use our sample, which is the next best thing. So when building confidence intervals with sampled means, the smaller the sample size, the smaller the degrees of freedom. The formula for the degrees of freedom is just n minus 1, because there's one parameter that we are left estimating, and the flatter the t-distribution. So as we saw here, it flattens out the smaller the sample size. The larger sample size, as a limit approaches infinity for you calc people, the degrees of freedom actually goes to infinity, and it becomes the normal model. So in other words, the wider we must go to obtain a certain level of confidence. So instead of going 2 standard deviations out to get 95% confidence, with a smaller degrees of freedom, we would have to go 3. I think it actually would, that's what this is showing here. So instead of going 1.96, if we had a sample size of 7, we would have to go 2.45 standard deviations. These are our critical values. And with a sample size of 4, he would have had to gone 3.18 standard deviations. So yeah, that's kind of nice. So those are showing the standard deviations for the critical values for a 95% confidence interval. So basically, the wider we have to go out in order to have a certain amount, 95% of the area underneath the curve. So, all right, for samples larger than 30, the t-distribution is very close to the normal, but we're still going to use those specific distributions, even though they become very close to the normal, because we know those statistics and we already have them. So once we get to 30, it becomes very close to the normal, but still we want to use the t-distribution models instead of the normal distributions, just because it's more precise. All right, so let's look at number 4. I'll do a few of the odd ones with you. So 4 and 18, the first two, and then you can do the backside on your own. Keep in mind the odd problems are in the back of the book, so you can grade yours, because I'm not really there to help you. All right, so T-models part 1. Using T-table software or calculator, we're going to use our calculator. Estimate the critical value of T for 95% confidence interval with degrees of freedom of 7. Well, that's what these numbers here are for, but this is just 3 different models. Well, really one of them is a normal, so it's 2 models, but we don't know what degrees of freedom for 7 is. So this would be when we have a sample size of 8. Here would be a sample size of 7 because the degrees of freedom was 6. So 95% confidence, it should be some value that is close to, let's see, yeah, 2.45, just as an estimate, because it's a larger sample. That means that it's actually going to be a little bit less than that, because it's going to be closer to our normal model. So it won't be as flat. So it'd be probably, if I estimate, it'd be about 2.4. So how do we find that exact value? Okay, so we're going to go to second variables, to the distribution menu. And we want to find critical value for 95% confidence. So we want to find when the area under the curve on the inside from the center is 95% with this certain parameterized T model. So instead of using the inverse normal model, we're using the inverse T model. See the T here? The T is for Gosset's distribution student model. So inverse T. All right. Now on this one, it doesn't give us. So let me quit out real quick. Notice that it doesn't allow us to do it from the left, center, or right, which is kind of stinks, honestly. If we would have done second variables and we went down to the inverse normal model, which is the third option here, then notice that it gives us the tail option from left, center, right. So when it doesn't give us that, like on older models of the 84 or 83, it's always defaulting to the left. That's how most standard tables work as well. So anyway, just keep that in mind. Just changes how we put our inputs. So inverse T model, the area. Okay, so if we want 95% confidence, so how much area do we want from the left? Well, we got 95% on the inside. So how much is on one of the tails? So there's 5% left on both tails. So one of the tails is 2.5. So we want 95 plus the 2.5 on this end, which is going to leave us with 2.5 on the other end. So the area we want is 0.975, leaving 2.5% on one side. Degrees of freedom. Actually, we could do the negative critical value if we want. We could have just done 2.5. We would have gotten the same answer, but that's okay. It just would have been positive, a negative instead of positive. Degrees of freedom, they told us that was 7, which means we had a sample size of 8. and hit paste, and it'll tell you how many standard deviations we have to go out, our critical value. So this is our critical value, which I estimated 2.4, but it's actually 2.36 because when we it actually starts to approach it pretty quick, I guess. So there's a big difference between having one more when the sample sizes are so small. It kind of makes sense. So instead of 2.45, it was actually 2.36, which again is still having to go wider than a normal model, but not as wide as when the degrees of freedom was 6. All right, critical value of T for 99% confidence interval with degrees of freedom, I think that should be 12. No, it says 102, so I guess we'll go with that. All right, so critical value, 99% confidence. So same thing, we're going to go second distribution, inverse T model, 99% confidence. So we could do 99.5, which would leave us with 0.5% on both ends. You also could just do this from the left tail as 0.005, and you'll get a negative critical value, but that's totally fine. All right, degrees of freedom, I said, was 102. Now, when the degrees of freedom are so large, with such a large sample of a sample size of 103, it's going to be really close. Remember, anything more than 30, they said it's going to be really close to a normal model. See, when we got to 30, it practically looks just like a normal model. So we should expect this one to be close to, was it 2.56 for the normal one? All right, so, or 2.65. I'm curious what it is with the normal model. So I'm going to go to inverse normal. I'm going to go with an area of 99% measured from the center, standard normal. All right, yeah, so we would have had to, with a normal model, we would go 2.57 standard deviations, but with a sample size of 102 or 103 degrees of freedom, it would be 102. Then we have to go 2.62. So there's a very slight difference because our sample size is so big. Again, there is a difference, and we should use those updated values from our technology, but if we would have used the normal model, it would have been really close anyway. Kind of a negligible difference, but we do want to do it. All right, what's the p-value? So what's the probability of having an observation with a t-score? Now, we're not talking about z-scores anymore. We're just using t-score. And the t just reminds you that we're sampling means and we're using a family of models, the t-distributions with a certain parameterized degrees of freedom. So to find that, if we know that it's 2.19 standard deviations above the mean, what's the probability of that occurring with 41 degrees of freedom, which is a sample size of 42? So we go to second variable store distribution. And now on this one, normally we would do the normal CDF, but now we're going to do the TCDF because we're using a T model. So it still stands for cumulative density function. Our lower limit in this case, we want to know when T is less than or equal to 2.19. So less than would be all the way to 0 or negative infinity. Our upper score is going to be 2.19. Degrees of freedom is going to be 41. So that's a new question that they're asking now that we're using T models instead of a normal model. And then we hit paste, and that's going to be 98%. So 98.3% is the probability of getting a value that is less than or equal to 2.19. Now, if that was a negative 2.19, then it would be much smaller. But because it was positive 2.19 and less than that, that's going to be most of them. So that would be a very common p-value, which would not be unusual at all. So maybe we set it up wrong would be kind of one thing that I would guess. All right, then what's the p-value for the absolute value of t? So we want to know when t or negative t is greater than this value. So that means it's a two-sided test. So we'll just double our probability when we're done with 12 degrees of freedom. So this one's going to be a little bit smaller. But again, we go to second distribution. We're going to go down to the inverse CDF. Not sure what just happened there. All right, so second variables distribution, TCDF. We want to know when it's greater than that. Okay, so I'm going to go from negative infinity to a negative 2.33, and then I'm going to double it. We could also go from a positive 2.33. I guess I'll do that. That's probably how you'd read it, to a positive infinity. So we'll just do 999. Degrees of freedom are going to be 12, so our sample size was 13. And we hit paste. Remember, when we're doing this, it's two-sided, so we're going to have to double our probability when we're done because we want to know both tails instead of just one. So the p-value for that would be 3.4%. And if that is less than our alpha level, so if we did an alpha level of 5%, this would be statistically significant and we could reject our null. Now, if we only wanted to know one side, that would be even more statistically significant because it would have half the p-value. All right, I think that might be it. Nope. Okay, so now we're on number 18. So parking. Hoping to lure more shoppers downtown, the city builds a new parking garage in a central business district. The city plans to pay for the structure through parking fees, like normal, during a 2-month period, which is 44 weekdays. So there's basically a sample size of 44 days. The daily fees collected averaged 126. So they have 44 daily fees, or daily averages, and they take the average of those daily amounts of fees that they collected, which gave us an average of 126. So basically, this is our sample size with a standard deviation of 15. So what assumptions must you make in order to use these statistics for inference? So our assumptions and conditions for inferences with means is very similar to what we're doing with proportions. And because of central limit theorem, it's actually easier. So the first one is randomization. So was our sample a random sample? Well, if we're talking about sampling 44 weekdays in a row, right? It was during a 2-month period. Was that a random sample of all the weekdays in a year? No. So what if they sampled this during a busier time? Let's say this is the business district. So I don't know when the busiest time for them would be. Let's say they did it during the holidays. So if it was during the holidays, people have days off during the holidays, or they're all going on vacation, and so there's less people that are going to be parking. Anyway, no matter what 2 months we picked, if it was just 2 months in a row, it's probably not going to be representative of what we would expect over a whole year. So this is not a random sample because we should have picked a random sample of days to do it throughout the whole year. All right, so it's not a random sample, but the question really when we're talking about randomization is this a representative sample? Well, if we believe these 2 months, the 2-month period was representative of what we would expect for the rest of the year, then it's okay to continue. But we would want to note it if we didn't. So we can still run the rest of our statistics, but we might want to note, just be honest about what happened. All right, independence. Let me delete this, we don't need that. Independence. So because we're not sampling with replacement, if somebody buys a parking for that day, that we can't sample that person again. They're not going to pay for parking twice in one day. So we're sampling without replacement as always. So the real question is that are we sampling without replacement with less than 10% of the population? So are the people that come in during those days, are they less than 10% of all the people that might come in altogether throughout the year? So that seems like a reasonable thing to say. So yes, we can override the independence assumption with the 10% condition because we're sampling less than 10% of the overall population. The next part is a large enough sample. This used to be the success failure condition, which guaranteed 3 standard deviations that were not cut off. But because it's not tied to the binomial model, the central limit theorem kind of acts a little bit differently with depending on the original population and the sample size. So the real question is it nearly normal with a smaller sample size, or if it is really skewed or like CO data, do we have a large enough sample in order for our sampling distribution model to become normal? So in this case, they don't tell us what the actual sample looked like, and we don't know what the population is either. So I would guess that the population would be slightly skewed because there are going to be some days that are far more busy. Maybe if there was a local NBA game going on, then they might sell a lot more tickets during game nights or something like that than they do regular working traffic throughout the day. So it's probably going to be skewed where some days they sell out and some days maybe they only have like 25% of people parking spots filled. So probably pretty far skewed. So if it is skewed and we think it is, then is our sample size large enough? Well, if we had a sample of 44, that's a moderately sized sample. It's kind of on the bigger end. So that should take care of the skewed data because the data is not really so heavily skewed that we would have to use like logarithms in order to straighten it out or anything like that, like CEO data, right? So it should be fine. So this should be a large enough sample to where the central limit theorem kicks in and allows us to make our sampling distribution model more nearly normal, or nearly normal enough, essentially. All right, so write a 90% confidence interval for the daily mean income of the parking garage will generate. So here are our sample statistics. The average, so our X bar, our average was $126 per day with a standard deviation of 15. So what we want to do here is we want to go to second distribution, or sorry, no, we're going to go to stat and then test. Now on this one, we would, we're doing an interval, so it's not a test. We're actually going to go to the intervals, and we're doing mean, so it's not a Z interval. We'd also do a Z interval if we knew the true population parameters, and we don't. So we're going to do a T interval. I'm going to look at the other ones real quick. We're not doing a one proportion Z interval because it's not a proportion. The samples are referring to means, but we are not using two samples yet, comparing two samples. So we're going to do a T interval. Now you have two options. You can either put the data in like your list, and then you just reference those list numbers, or you can give the actual sum or statistics, which is what we were given. So our X bar was 126, and our standard deviation, the S of X, again, notice how it's telling you it's the standard deviation of X, which comes from a sample. So the sample standard deviation is 15. So what's nice is the calculator kind of guides you with what you need to put in. All right, what was our sample size? 44, so the degrees of freedom would be 43, but they asked for N, not DF, so it does that for you just in case you forget, which is also really nice. Confidence level, we wanted 90% confidence. Then hit calculate, and the calculator does all the work. All right, so if we write that interval, you can just copy that down. So it's $122.2 to $129.8. All right, interpret the confidence interval in context. So we would say that we are 90% confident that the true proportion is anywhere between, and I'll have to go back to that one. So it'll keep those values. So if you do have to run it again, it's not that big of a deal. See, the values are all the same. So just hit calculate. All right, so we are 90% confident that the true average, daily average for the year for the parking lot will be anywhere between $122.2 and $129.8. What does 90% confidence mean in context? So that would mean that 90% of samples or confidence intervals created with this sample size and this method would successfully capture the true proportion. So a consultant advised the city on the project projected that the daily average would be $130 a day. Based on our confidence interval, do we agree with him? Well, 130 is outside of our confidence interval. So if that was, so we disagree, right? It's possible that the true proportion is 130, but that would only happen with an error, a false positive error, or a type 1 error of, if we had 90%, that would be 5%. So 5% of the time, we could have missed it in this case with a one-tailed test using a 90% confidence interval, but it's unlikely. So we're going to stick with our confidence interval and say we think he's off. We think it's actually less than that. So he's trying to tell them that they're going to get more money when they're actually going to be, we think we're going to earn less money, which would mean that we'd have to raise the prices in order to raise the amount of money for the project. Someone suggests that the city use the data to create a 95% confidence interval instead of 90%. So how will this interval be better for the city? So if we go from 90% confidence to 95% confidence, it's always a trade-off between confidence and precision. So when we want to have more confidence, we have to have a wider confidence interval, which is a larger margin of error. So we'll have less false positives in that case because our region is much larger, and we'll successfully capture the true proportion 95% of the time, but it also means that our range of values is going to be larger because we have a larger margin of error. So how would it be better for the city? We don't actually have to calculate it. So we would have a better idea of the range of values. We're more likely to capture the true proportion. We have more confidence. All right, how would the 95% confidence interval be worse for the planners? It's a larger range of values, which means we to be on the safe side, we're going to have to set the cost that we are planning on charging people even higher is what's going to end up happening. So how could they achieve an interval estimate that would better serve their planning needs? So how do we improve our estimates? Well, as always in sampling, we can get a better sample. Not just gathering data properly by using, data from the whole year, but really in this case, because we can't jump through time, we just want to increase our sample size. So gather data for another month or another 2 months, and that will decrease our margin of error. If we did a 4 times the sample size, then it would cut our margin of error in half, and so it would shrink our confidence interval in half because it's the inverse square root law going on in effect.